Okay, so optimization. This problem here is a little more difficult than the other optimization problems that we've dealt with because we've got to create our own picture. There's no set um, equation. It's not like a cost, so we got to set up our own. So we're going to actually read it and create their picture ourselves. So that's going to be one of the most challenging parts about this. So it says Jane is 2 miles offshore in a boat and wishes to reach a coastal village which is 6 miles down a straight shoreline from the point nearest the boat. She can row 2 miles an hour and she can walk 5 miles an hour. Where should she land her boat to reach the village in the least amount of time? Okay, so the picture is critical here. Okay, so we've got this shoreline that we're going to be dealing with. So here's the shoreline. Then we've got, let's say this is our little village right here. Okay, so this is the point right here. This is the village. Okay, now it says Jane's in a boat 2 miles offshore. Okay, so we're going to put, and it says that she's 6 miles from the village. So this distance from right here to right here, this here is 6 miles. Okay, she's in a boat here, so we'll draw a little boat. And this boat right here is 2 miles offshore. So from here to here, this is 2 miles. Okay, it says, where should she land her boat to reach the village in the least amount of time? So she wants to get from here, from this point here, to the village as fast as possible. Okay, now she can row the boat 2 miles an hour and she can walk 5 miles an hour. So looking at that, if she wants to use the least amount of time, she's going to want to do more walking than she is rowing. Okay, now the problem is that if if she does this and goes like that, that's going to take longer, okay, because she's going to be not making forward progress towards the village. So the shortest distance between 2 points is a straight line. So this is the shortest distance, but it might not be the fastest because she can only row 2 miles an hour and she can walk 5 miles an hour. So she's going to want to do more walking than she is rowing. So our our line that she's going to want to take is going to look something like this, where she's going to come in, land somewhere, and then walk the rest of the distance to the village. And then they want to know, where is she going to land her boat? So how far from where she is now, this distance from here to here, how far does she need to land her boat? Let's call that X, to reach the village in the least amount of time. Okay? So again, we know that we're going to want to do this distance from here to here is going to be bigger than the distance from here to here because we can row like more than half the speed that we can walk. So we're going to want to do more walking. It's faster to walk than it is to row the boat. Okay? So, what are we optimizing? Well, we're optimizing our time. Okay? Well, so we all know that velocity is distance over time, right? So if we want to change to time, time is equal to what? If we rearrange this equation, time is going to be equal to distance divided by velocity. Okay? Now, what we're trying to optimize is our total time. So total time is going to be equal to, let's say, time rowing plus time walking. Okay, so that's what we're trying to optimize. Okay, so we've got our optimization equation. Now, we don't necessarily have what we would truly call a secondary equation, but we do have to get it all in terms of one variable. Okay, so using what we've got here, our total time is going to be distance over velocity rowing plus distance over velocity walking. Okay, because that one we know. Now we also know that this distance right here, this distance that we're going to be walking, since this is the distance this way that we're going to be rowing, and this is 6 miles, this is going to be what's left over, which is 6 minus x. So this is the distance that we're going to be walking. This is distance walking. This right here is the distance that we're going to be rowing. Okay? And since this is perpendicular, we have a right triangle, so basically we can set up Pythagorean theorem and solve for our hypotenuse, which means our distance rowing is going to be the square root of 4 plus x squared. Okay? So now that we have our distances, we can plug it into our total time equation, which means our total time equation is going to be the distance rowing, which is 4 plus x squared over 2, plus 6 minus x over 5. So that is our equation for total time it's going to take. Okay? So how do we minimize that? Because that's what we're trying to do. We're trying to minimize, use the least amount of time we're minimizing. Well, how do you find maximums and minimums? You take the derivative and set it equal to 0. So to make my life easier, I'm going to rewrite this as 1/2 the square root of 4 plus x squared plus 1/5 times 6 minus x. Okay, because remember, dividing by a number is the same thing as multiplying its reciprocal. So when I go to take the derivative, it's going to be much easier if I have it in this form. And when I take the derivative, when I get t prime, I'm going to get 1/2 times the derivative of the square root, which is going to be 2 square root of 4 plus x squared, and then the derivative of the inside on the top, which is 2x, plus 1/5 times the derivative of 6 minus x, which is -1. Okay, simplify. This 2 and that 2 divides out, so I get x over 2 square root of 4 plus x squared minus 1/5, set it equal to 0. So we got to find the zeros. Okay? So first step, I'm going to move the -1/5 to the other side. So I get x over 2 square root of 4 plus x squared equals 1/5. Then the easiest thing to do here is to cross multiply. So you get 5x equals 2 square root of 4 plus x squared. Then you can square both sides to get rid of that root, which gives you 25x squared equals 4 times 4 plus x squared. Multiply the 4 in. Then subtract the 4x. You're going to get 21x squared equals 16. divide both sides by 21, which means you get x equals plus or minus 4 over the square root of 21. Okay? Now, we don't have to worry about the negative one because we can't have a negative distance. So we just deal with the positive one. Okay? So now, that is one of our critical points. So let's check it out. Well, this is approximately, if you plug it into a calculator, it's 2.12. Okay? Now, let's check our endpoints just to be sure. Okay? So t, the time that it takes when we plug in 4 over the square root of 21. That's going to be, that's 2.12. That's our time. Okay? Oh, sorry, I used the wrong number. I didn't do this right. This is actually, sorry, I knew something was wrong when I plugged in the calculator. This is 0.87. That's the distance, the approximation. Okay, 2.12 is the time. Now, if we looked at time equals, or the distance at 0, if we plug in 0 distance, which means she doesn't go any direction in the x, she just goes straight in, it would take us 2.2 hours. If she rode the entire time, which means she landed right at the village, it would have taken her 3.16 hours. So the reason I was checking my endpoints is because it might have been faster for her to actually just row straight in. And it almost was. If she just rode straight into the shore and then walked the rest of the distance, it would have been 2.2 hours versus if she goes this distance of 0.87 miles and then walks the rest of the distance, is slightly faster. Okay? So the distance, this is, of course, our least amount of time at this distance. And that's how you do it. And the hardest part about this problem was actually drawing the picture, trying to figure out what the scenario looked like. Okay? And that's why I work a lot with these types of word problems with my pre-cal students to get them ready for stuff like this, where you actually have to figure out what they're trying to get you to draw.